connectedness. So what is connected metric space? Suppose we have a metric space Xt. It is said to be connected if the only sets which are both open and closed in this metric space are empty set phi and the full space X. The subset A of a metric space Xt is said to be connected if A is connected space when considered as a metric space or subspace with the induced topology. It means the space A together with delta is connected, where delta is the restriction of the metric D on X to A. For example, any interval in R is connected. Interval may be of the form open interval AB, it may be semi-closed interval which is open at A and closed at B, semi-closed interval of this type, closed at A and open at B, and closed interval AB. Then all these intervals are connected on the set of real number R. Here A and B are elements of R, means A and B are real numbers. One more example is that metric space having only one element is connected. Also, the unit circle, which is defined as set of ordered pair xy, so that x square plus y square equal to 1, is connected in two-dimensional real space. Any real line is connected in R square. If we write L as xy such that x is greater than or equal to 1 and y equal to 0, it is connected in two-dimensional real space. If we consider a set X, which is a set of real number in which the singleton set 0 is not included, and if we consider this metric space of all non-zero real numbers, because 0 is not included in it, with the usual metric defined as dxy equal to modulus of x minus y, and if we define a set A to be set of all the points x which are greater than 0, and we define a set B as a set of all the point x belonging to x such that x is less than 0, then the pair AB is a disconnection. Means this set A and B are not connected. Clearly these are open intervals, because x is greater than 0 means 0 to infinity, and it is less than 0 minus infinity to 0, and these are disjoint sets because nothing is common in these two sets. So these are disconnections. Also we say that x is equal to A union B. So we can say that a space X is said to be connected if it can be divided into two non-empty disjoint open sets, because in this example you have seen that A and B are non-empty, also disjoint open sets. So it is clear that a connected space is a space that is one piece and cannot be split into parts. Now, characterization of connected spaces. A topological space X is said to be connected if and only if every continuous function f from X to this set which consists of plus 1 and minus 1 is a constant function. Or we can also say like this: a subset A of X endowed with a subspace topology is connected if and only if every continuous function f from A to this set consisting of 1 and minus 1 is a constant function. So we have two parts. If X is connected if every continuous function is a constant function, and if every continuous function defined like this is a constant function, then it is connected. So first of all, we assume that X is connected space and f is continuous function. Now we want to show that it is constant function. Suppose f is not constant function, it is a non-constant function. It means, what do you mean by non-constant function? If there exist distinct points x and y in x, then fx is not equal to fy. For any two values which if x is not equal to y, then fx is also not equal to y. It means a function is not constant, it is a non-constant function. Because in the image here we have range set, we have 1 and minus 1. So without loss of generality, we may assume fx equal to 1 and fy equal to minus 1. Here 1 and minus 1 are distinct points and fx is not equal to fy. Suppose A is inverse image of this singleton set 1 and B is a set consisting of inverse image of minus 1. Clearly A and B are disjoint because nothing is common in them. Also these are non-empty and A and B are open and closed. These are both open and closed, and so we can write x equal to A union B, because we know that if f is a continuous function which is given to us, pre-images of open sets under f are open sets. So this is contradiction to the assumption that x is connected, because we have expressed x as a union of two sets which are disjoint, non-empty and closed. So this contradicts the assumption of connectedness. It means f is constant function, because in the last slide we have explained that a space is connected if it cannot be divided into two non-empty disjoint open sets. Now the converse part. For the converse part, suppose f is constant. Now we have to prove that x is connected. Suppose we assume that x is not connected. If x is not connected, it means there exist two disjoint proper non-empty subsets A and B in x, such that A and B are both open and closed in x, and x is equal to A union B, and A intersection B is not equal to phi. Suppose we define a function f from x to the set consisting of 1 and minus 1 as fx equal to 1 if x belongs to A and minus 1 if x belongs to B. Clearly this function is continuous function because A and B are open sets. Here it is given to us A and B are open set, so it means f is continuous. Also clearly we see that for all the points of the set A, the fx is equal to 1, and for all the points on the set B it is minus 1. So it assigns different values in A and B. So this is a contradiction to the assumption that f is constant, because here it means that by the definition of f it is clear that this is not a constant function. So it means x is connected. Now one theorem, subset E of R is connected if and only if it is an interval. So in the first slide also we have given an example that intervals on the real line are always connected. So suppose that E is an interval. Now we have to show that R is connected. Suppose we consider two arbitrary points A and B in A and B in this open interval, in this interval E, such that A is less than B. Now we need to show that any point X lying between A and B is also in E. Because E is an interval, so any point between A and B must lie in E. Suppose there exists X in interval AB that is not in E. So Suppose this x is greater than a. We can assume it without loss of generality. Because E is an interval, it contains all points between a and x. Because x is not in E, it must either be less than a, because x does not belong to E, or it must be greater than b. But this contradicts our assumption. Therefore, there are no points in AB that are not in E. Hence, every point in AB lies in E. It means E is connected, since for any 2 points in E, all points between them are also in E. So, we can say that if E is an interval, then it is connected. Now, the converse part. Suppose E is connected subset of R. Since E is an interval, we have to prove that E is an interval. And it is given to us that E is connected subset of R. We assume that E is not an interval. It means there exists point A, C and B in E, where C lies between A and B, but the entire interval AB is not contained in E, because we have considered that E is not an interval. Suppose we write A equal to minus infinity to C intersection E and B equal to C to infinity intersection E. Clearly, A is non-empty, because here the points are minus infinity to C. So A lies between minus infinity and C, and E is A to B. So A is non-empty because A belongs to A. Similarly, B is non-empty because B belongs to B. Also, A and B are disjoint. There is nothing common in A and B, because if there were a point x belonging to A intersection B, then x would be both less than C, because it belongs to A. So x should be less than C, and it should be greater than C because x belongs to B. So which is a contradiction, because x cannot be both less than C and also greater than C. So it means A and B are disjoint. Also, A and B are open set, because for any point y belonging to A, because A is given to be minus infinity to C intersection E, we can find an open interval y dash C containing y that is entirely contained in E. This is by the definition of open set. So instead of wall, because we are considering a real line, we have considered open interval. Similarly, for any set Z belonging to B, because Z belongs to C to infinity intersection E, we can find an open interval E to Z dash containing Z that is entirely contained in E. It means E is not connected, because we have proved that A and B are non-empty, disjoint and open sets. So this contradicts the assumption that E is connected. So if E is connected, then it is an interval. Now one more result. Let X3 be a metric space and AB be two connected subsets of X such that A intersection B is not equal to 5. Then A union B is connected. Here A and B are given to be connected subsets of X and whose intersection is not equal to 5. Suppose C belongs to A intersection B, because this is non-empty, so let C belongs to A intersection B, and F is a mapping from A intersection B to this set consisting of 1 and minus 1 be continuous. Because A is connected, the restriction of F to A denoted by FA is continuous function on A. By the connectedness of A, this restriction of F to A must be constant on A. It means Fa should be equal to Fc, value of F at A should be equal to value of F at C for all points in A. Similarly, by connectedness of B, the restriction of F to B denoted by Fb is a continuous function on B, and by connectedness of B, this restriction must be constant on B. Means F is must be constant on B. So Fb is equal to Fc for all B belonging to C. So now we can extend the function F to union A union B by defining it as follows. Because if x belongs to A, let Fx is equal to Fa for all A belonging to A, and for x belonging to B, let Fx is equal to Fb for any B belonging to B. So it means we have shown that any continuous function F from A union B to this set is a constant function from here, and so this is a constant function as it takes the same value at all points of A union B. Hence A union B is connected. Now one more result. Let A be a connected subset of a metric space Xt, and A is a subset of B, and B is a subset of A bar. A bar is the closure of A. Then B is connected. Suppose F is a mapping from B to this set consisting of 1 and minus 1. Suppose this is continuous function. We are given that A is connected subset. So the restriction of F to A, which we denote by Fa, is continuous function on A. So by the connectedness of A, Fa must be a constant function on A. It means Fa equal to 1 for all A belonging to A. Let B belongs to B. Since F is continuous at B, given the open set Fb, in this set there exists an open set U containing B such that F of U is a subset of this set consisting of Fb. Since B belongs to B, which is contained in A bar, means closure of A. Here it is given to us. So B is a limit point of A. In particular, this means A belongs to A intersection U. So we find that F of A belongs to F of B, or F of B equal to 1, or we can say 1 at A or 1. Thus F is a constant on B. Let X3 be a connected metric space and G be continuous map, then Gx is connected. We can prove it in different ways. This is one method and this is another method. Suppose F is a mapping from Gx to the set consisting of 1 and minus 1. Suppose this is a continuous function on Fx. Since F of G means composite mapping of F and G from x2 plus minus 1 is continuous and x is given to be connected, it means F of G is constant on x. It means F is a constant function on Gx. It means Gx is connected. Or we can prove it like this also. Suppose Gx is not connected. Then there exists a proper subset V of Gx which is both open and closed in Gx. Because F is continuous, therefore G inverse B, V and G inverse of G, a complement of V means Gx minus V are both non-empty, closed and open in X. And these form disjoint pair of non-empty open sets in X. Therefore, this contradicts the assumption that Gx is connected. So, our assumption that Gx is not connected must be false. So, it means we can say that Gx is connected. So, we can say that if G is a continuous map from X to Y, and if X is connected, then G of X means image of X under G is also connected. This line is not required here because assumption that Gx is not connected must be false. It means Gx is connected. Now we will prove one more result, that metric space Xt is connected if and only if only subsets of X that are both open and closed are X and phi. Suppose Xt is a connected metric space. Now we have to show that the only subsets of X that are both open and closed are X and phi. Suppose M is a subset of X that is both open and closed. This is other than X and phi. Suppose Y denotes the complement of M. Since a set is open if and only if its complement is closed, it means Y is both open and closed, because M is both open and closed, therefore Y is also both open and closed. It means X is disjoint union of M and Y. Because M is non-empty, Y is non-empty, M is open, Y is open, M is closed, Y is closed, and X is equal to M union Y. So X is disjoint union of M and Y, which are both open and closed. Then by the definition of connectedness, M and Y cannot be both non-empty. So one of M and Y is the empty set and the other is X. It means M is either phi or X. Now the converse part. Suppose that only subsets of X that are both open and closed are X and phi. Now we have to show that X is connected. If X is not connected, then it would be written as disjoint union of non-empty open subsets of M and Y. But then M would be non-empty proper subset of X that is both open and closed, contradicting the hypothesis. It means X must be connected. Thank you.